So for the rest of this lecture, what we're going to do is talk about some kind of structures which are called trusses. So trusses are a special kind of structure. And let's see what makes a truss. So a truss is composed by bars. Sometimes you can call them rods, can be cables, can be wires, or the bar itself can be called a truss. So let's call them bars. They're composed by bars, and these bars are connected by frictionless pins. So the pins that connect the bars, let's call them the joints. Just to give it names so that I do not need to say the pin that connect the bar. So you have two bars like this, 1 and 2, and they are connected through a pin, a frictionless pin. You see? All right, so I have bars connected by pins. That's one thing. And it is supported also by frictionless pins. So it can be supported by what we call the hinge, or what we called a roller. So the bars are attached to the ground either through hinges or through rollers. So they are connected by pins, they are supported at pins, and they are loaded only by concentrated forces acting at the joints, at the pins. Can be at the joints or at the hinges and roller. So, what does it mean? It means that you got your things made of all these bars. So let's draw an example. So something that looks like that. So I have a bar like this and a bar like this. I have pins here, here, and here. This one here is a hinge. This one here is a hinge. This one here is a joint. And right here, I have a force applied. The force can only be applied at the joint. In order to be a truss, I cannot have forces applied halfway through the truss. I cannot have distributed load in these things. The only way that I'm dying. The only way that I can load this structure is by applying loads at the pins. So that is a truss, something that looks like this. Actually, let me make a roller here. Something that looks like this. I can make it as complicated as I want. Something that looks like this is a truss. Each of these things are bars. These are the pins that connect them. These are the supports, a hinge and a roller, and the forces are only applied at the pins. I can also have a force applied here, P, okay?
When you say apply, do you mean like we can only think about the forces at that point?
Yes, you have to imagine that all the forces that load the structure are applied at that hinge. You have to imagine that somebody comes in, and this is the hinge, and hangs a basket of, rocks from here. Notice not wood. I was gonna say a basket of bananas, but I caught myself at the last moment. Okay, so he hangs a basket of rocks right from this pin. The load only acts on the pins. I do not directly apply load to the bars. If I applied load directly to the bars, like if I sit on a bar, I made a beam, not a truss. Okay? Something that looks like this. This is not a truss. Not. This is a beam. Because the load is applied here. You see what happens to this guy? Okay. So these are the rules of what are trusses. So they are connected by these frictionless pins. We sketch them like this. We sketch the bars like this and the pins like this. These are hinges and rollers. And the thing that makes life easy for trusses is that each bar is a 2FM. This means it's a 2-force member. What it means is that for each of these bars, the only place where the forces can be applied are at the end. Let's consider a bar, and let's consider point A and point B. Okay, so now I have a bar. Let me get rid of my pen. I have a bar, and the only place where I can apply load in this bar is at the two ends, point A and point B. All right, so I can only have a force FB and another force FA. Now, in order for this to be in equilibrium of my two-force member, I need to have that the sum of the forces must be 0. Right? Otherwise, this bar is not going to be in equilibrium. So what it means is that FA plus FB must be 0. And this means that FA must be equal to minus FB. So already this one is wrong. So this one cannot be, because I need to have FA equal to minus FB. So I already know this just from balance of the forces. This is the same as when we had just a bar in axial loading, and we said the force on this end must be equal to the force on this other end. But now we graduated to the two-dimensional world, so we don't need to worry about just, is the bar going to move left and right? We also have to worry about the fact that the bar is going to rotate in the plane. We do not want the bar to spin in the plane. So it must also be true that the sum of the moment, and let's do directly moment z. Actually, let's do the sum of the moment. What the heck? This is so simple that we can even do vector. The sum of the moment must be 0. So sum of the moments, the first thing that you say is, you're missing something there. What am I missing? Pivot point. With respect to some pivot. So the first rule of choosing a good pivot is choosing a pivot that eliminates unknowns. If I choose my pivot at A, I don't need to worry about the force acting at A, because the moment of FA with respect to A is what? Zilch. So if I do the moment with respect to A as my pivot point, then all what I need to worry is RAB cross FB. This I want to be 0. How do I make it so that the moment of this force with respect to this pivot point is 0? Exactly. What must happen is that I cannot have a force like that, another screwed up thing. Absolutely not. I need to have a force like that. You see? Because that way, nothing makes me rotate with respect to pivot point A. So this thing means that FB must be parallel to RAB. You see? So the only way that a two-force member can be in equilibrium is if it's loaded simply along its axis, like that. And this is the only way. So, and remember that FA is equal to minus FB. So it must be loaded like this. That's the only way that it can stay there and not start moving to a different continent. So it's pulled this way and it's pulled that way, and this is in equilibrium. Okay? So what is the only thing inside this bar? What kind of force? Transverse force? An axial force? You can take hints. Okay, it's an axial force only. The only thing inside the bar is an axial force. And that's why we can deal with it now, because we know how to deal with axial forces. What is the axial force? So there is only an axial force, N, inside the bar. If I cut here, the only thing I'm going to find inside that bar is an axial force in the bar. And it's constant, because the only thing acting on this bar is a force here and a force here. Any way I cut, I'm going to find the same axial force. Because it's a bar that goes from A to B, let's call the NAB, the axial force in bar AB. So if the axial force is positive, what does it mean for the bar? Is it being pulled or pushed? Pulled. So a positive axial force means that the bar feels pulled. A negative axial force, it means that the bar feels pushed. Once I give you the value of N, 3 newtons, minus 7 newtons, plus 3.2 newtons, I tell you everything of what's going on inside the bar, because the only thing that the bar can carry is an axial force in trusses. And just by giving you the magnitude and the sign, I tell you, is it pulled, is it pushed? Are we good? That's why doing trusses is so nice. And by the way, a very important point. What does the pin feel? Say that this is my bar, and it's stuck between 2 pins. Imagine that your hands are the pins at the end of the bar. If there is a positive axial force in the bar, and the bar is pulled, what do the pins feel from the bar? Do they feel pulled into the bar, or do they feel pushed by the bar? They feel pulled. So if you have a pin and is attached to a bar, a positive axial force, it means that it pulled the pins toward the bar. So the pin, positive axial force, pull pin towards the bar. You can kind of see that if I have, I'm compressing too much. If my bar feels compressed, imagine these are your hands, you feel pushed by the bar. So a negative N means that the bar pushes on the pins, right? So if you have N negative pushes the pin. So, for instance, if I have a pin like that and it's attached to this bar, and this bar, and I tell you that N here is 3 newtons, N here is minus 2 newtons, and N here is whatever, 5 newtons. What this means is that the pin feels 3 newtons coming up in the direction in which the bar was, 2 newtons pushing from that way, and 5 newtons pulling along this direction. You see what I mean? Okay? Store this in your brain someplace. Okay? Okay, so what we're going to do now is we're going to do a problem. A truss problem. We're going to do a simple truss problem and see how we solve it.